In the grand, silent theater of the cosmos, there are objects of such immense power and profound mystery that they challenge the very limits of our understanding. Imagine a place where the familiar laws of physics seem to break down, where time itself can stretch and slow, where gravity is so overwhelmingly strong that nothing, not even light, can escape its grasp. These are not creations of science fiction. They are real. They are scattered throughout our universe, lurking in the dark, silent voids between the stars. We call them black holes, one of the most extreme and fascinating phenomena in the known universe, a place where gravity always and completely wins. The life of a star is a constant epic battle, a struggle between two opposing forces. On one side there is the incredible outward pressure generated by nuclear fusion in its core. This is the process that makes stars shine, fusing lighter elements into heavier ones and releasing tremendous amounts of energy. On the other side, there is the relentless, inward pull of the star's own gravity, trying to crush it into the smallest possible space. For millions, or even billions of years, these two forces are locked in a delicate balance, a cosmic stalemate that allows the star to exist in a stable state, warming the worlds that may orbit it. But this balance cannot last forever. For the most massive stars, the end comes in a truly spectacular fashion. Eventually, the star runs out of fuel for its nuclear furnace. When the fusion in the core stops, the outward pressure suddenly vanishes. With its primary defense gone, gravity wins the long war. And it wins catastrophically. The star's core collapses in on itself in a fraction of a second. That implosion triggers a titanic explosion, a supernova, so brilliant it can briefly outshine its entire galaxy, scattering the star's outer layers across space. But the fate of the core is much darker. If the remnant is massive enough, more than about 3 times the sun's mass, no known force can stop complete gravitational collapse. It continues to crush itself down, smaller and smaller, past the density of an atom's nucleus, until all its mass is concentrated into an infinitely dense point, a singularity. To understand the immense power of a black hole, we must first talk about a concept called escape velocity. Escape velocity is the speed an object needs to travel to break free from the gravitational pull of a celestial body, like a planet or a star, without needing any more propulsion. To launch a rocket from Earth so that it escapes our planet's gravity and travels into deep space, it needs to reach a speed of about 25,000 miles per hour, or 11.2 kilometers per second. If it goes any slower, gravity will eventually pull it back down. Every object with mass has an escape velocity, and it depends on 2 things: how massive the object is and how far you are from its center. The relationship can be described with a simple, elegant equation. V equals the square root of 2gm over rv is the escape velocity. G is the gravitational constant, a fundamental number that describes the strength of gravity throughout the universe. M is the mass of the planet or star. R is the radius or the distance from its center. You can see from this formula that if you make an object more massive, increase m, or shrink it to a smaller size, decrease rr, the escape velocity needed to leave its surface gets higher and higher. It becomes much harder to break free from its gravitational grip. Now let's apply this to the formation of a black hole. When a massive star collapses, its mass stays the same, but its radius shrinks to an incredibly small size. As r gets smaller and smaller, the escape velocity from its surface skyrockets to astronomical figures. Imagine squeezing our sun down to the size of a small city. The escape velocity from its surface would become enormous. A black hole is what happens when this process is taken to its ultimate extreme. The core collapses so much that the escape velocity at a certain boundary, the event horizon, becomes greater than the speed of light. This is the defining feature of a black hole. The speed of light, about 300,000 kilometers per second, is the ultimate speed limit in the cosmos. Nothing can travel faster. Because the escape velocity at the event horizon of a black hole exceeds this cosmic speed limit, absolutely nothing can get away. Light that enters the event horizon cannot climb back out. A spaceship, no matter how powerful its engines, cannot escape. This is why we call them black holes. They don't reflect or emit any light. They are the universe's perfect prisons. And the event horizon is the wall from which there is no return. For centuries we thought of gravity as a mysterious force, an invisible rope pulling objects toward each other, as described by Isaac Newton. But in the early 20th century, Albert Einstein gave us a completely new way to understand gravity. In his theory of general relativity, space and time are not separate, static concepts. Instead, they are woven together into a single, dynamic, four-dimensional continuum called space-time. Imagine this space-time as a giant, flexible sheet, a cosmic trampoline. This fabric of the cosmos is the stage upon which all events in the universe unfold. According to Einstein, gravity is not a force in the traditional sense. Instead, it is the effect of mass and energy warping this fabric of space-time. Picture a heavy bowling ball in the center of a trampoline. It makes a deep depression in the fabric. Roll a smaller marble nearby, it won't go straight. It follows the curve, spiraling inward. To an outside observer, it looks like a pull. This is Einstein's gravity. The Earth orbits the Sun not because of an invisible rope, but because it's following the curve in space-time made by the Sun's mass. A black hole is the most extreme version of this idea. If the Sun is a bowling ball, a black hole is far heavier, ripping a hole right through the fabric. The curvature near a black hole becomes a bottomless well. The event horizon is the edge where the slope goes vertical. Cross it and all paths lead down to the singularity at the center. Space itself is flowing in faster than you could ever move. This geometry of space idea opens huge questions. Black holes are frontiers of physics, not just vacuum cleaners. What happens to time inside a black hole? What is the singularity? A point of infinite density where our laws break. Could black holes be gateways to other regions or even other universes? We don't have the answers yet. But by studying these dark, enigmatic objects, we keep testing the limits of knowledge and searching for a fuller theory of the cosmos. The universe whispers its secrets. Black holes shout them. We just have to keep listening.